Hi, Stuart.
Ryan, how you doing?
Pretty good. How are you?
Good. Good.
Awesome. How did you like the speaker series on Friday?
I thought she was very good.
Yeah, I was really intrigued by it. That was actually my first speaker series that I've attended, just because I've never really had time on Friday nights.
No, I think she, it was very well laid out with the slides and the text in terms of just walking through, building it up.
Heard in her voice that she was very knowledgeable in her area.
Mhm. Yeah, I think she went back and I got her PhD in Italy a couple of years ago, and she's been at Goddard, I think.
Okay. Yeah. So Deborah won't be joining us tonight?
No, Ann said she would. She watched the movie with me.
Okay.
She's getting one.
Gotcha.
And Deborah had her operation yesterday and did fine. So I think she'll.
Okay. All right. That's good.
Emailed me this morning that she's doing fine.
Okay.
But I have a feeling she's not. She wasn't planning to come. Just
right. Yeah, I got that in her email.
Mm.
Yeah. So we'll give it like a minute or so for ON to show up.
Okay. What struck you when your question had to do with was it a question of the smallness or the?
It really wasn't a question. It was just more of like something that
comment
sparked my interest. It was the orders of magnitude thing. We have
what?
like 10 to the 20 EV, which is just like an extraordinarily huge amount of energy. From these gamma ray bursts. I think that's what they came from.
Cosmic ray bursts.
Cosmic rays. Okay. Yes. Mm-hmm.
So I guess if I understood what she was saying is something, we don't know what it is. Maybe it's different all the time. It hits the Earth's atmosphere and then it fragments.
That's right. And I think we had looked at this maybe a few weeks ago on Sci Fi Explained. Mm-hmm. The cosmic rays that interact with the particles in the Earth's atmosphere form these different particles like muons and pions and neutrinos.
Right.
And I know like muons, for instance, are great particles to do experiments with like special relativity. We were able to confirm the effects of special relativity with these high energy muons that come through the atmosphere because they have a certain half-life. And according to the muons, they should decay pretty rapidly. But here on Earth, we observe them traveling all the way down to the surface. Mm-hmm. And that's just because of time dilation, one of the effects of special relativity.
Mm-hmm. That's interesting.
Mm-hmm.
So the energy comes from breaking up these rays, breaking apart particles and releasing energy. Is that where the energy?
Yeah, let me bring up this article again. I think that we looked at a few weeks ago.
I can't remember what movie it was related to.
Yeah, I don't remember either. I'd have to go back and check the YouTube.
Yeah.
Okay. So when a proton, and so protons will be emitted, they're one of the components of the cosmic rays. Mm-hmm. The proton splits into all of these different subatomic particles. Mm-hmm. Okay, here's ON. So we have the pion, the positive charged pion going on one side, negatively charged pion, and then in the middle, we have a neutral pion and a neutron. And then these pions further decay into muons and neutrinos, and then these guys decay into photons and electrons. So the proton's really being ripped apart into all of these different tinier particles.
Mm-hmm. And that's where the energy comes.
Yeah. So this is like E equals mc squared. You have the mass of the proton is now being converted into raw energy. And so I think someone would have to do the calculation for me. I'm not up for it, but I believe that if you added up all the masses of these pions and electrons, it would be less than the mass of the proton.
Because the difference is the energy.
Right. So you're changing mass into energy plus some extra residual mass.
Mm-hmm. But where's all that energy gets dissipated in the atmosphere?
I think so. Let me continue reading here.
And we're talking about cosmic rays from the talk last Friday.
Yeah, so some of the energy is light. And so these are the pair of photons at the bottom here. So the proton itself has enormous amounts of energy. And what makes it high energy is it's coming from the sun and also from just outside, like in our own Milky Way. So outside of our solar system, you can still have cosmic rays. And some of these may be emitted from, let's say, the supermassive black hole in the center. I think our galaxy, it has like an active galactic nucleus. So let me refresh my memory here, because it's been a while since I've studied these. Active galactic nucleus, yeah, is basically a huge ray that's emanating what looks like from the center of a black hole. We all know that's impossible. You can't have radiation coming out of a black hole. It's really just the energy being translated by the potential energy is now being converted into visible light, and that's what's being ejected from the center of these galaxies. I believe
from the black hole,
the same thing.
From the black hole in the center of the galaxy.
Yeah, it's coming from the accretion disk. It's not really coming, from the beyond the event horizon. So okay, we would have something
the
like
accretion
this.
disk is the matter that's orbiting around the black hole, but
that's right.
Isn't falling into it.
Yeah, so we could get high energy photons from these big AGNs, abbreviation. And then, of course, thank goodness we have a magnetosphere to shield ourselves from the solar wind. Otherwise, our atmosphere would just be stripped away and we'd suffer from acute, UV radiation, maybe even some X-rays, because the sun does produce a fair amount of X-ray radiation. Would not be good for us human beings and other organisms. So we have our magnetic field to deflect these rays, but then, of course, it's not totally impermeable. At the poles, we have these little weak spots. And when solar radiation, those particles enter the Earth's atmosphere around the poles, we get the northern lights.
Beautiful
it's a very
northern
cool
light
phenomenon.
What do they call it in the southern hemisphere? The southern lights, or do they call it, is it still the aurora borealis?
They do call it the southern lights, in fact.
Okay.
Yes. So aurora is any light that looks like this emitted close to the poles. I think I have let me see if I can pull it up. A picture saved somewhere. Oh, you know what? It might be on my other computer. But I remember I'm not sure if I had mentioned this, but I remember my first time seeing the Northern Lights. It was pretty bizarre. I was out in Jackson, Wyoming. I was taking some astrophotography with Sam's camera. And when I went to go look at the image after it had saved to the computer, because I had a long exposure, maybe like 20-second exposure, I uploaded to the computer and I saw a very faint green glow on the horizon. I was like, that is strange. What is that? I showed it to Sam. And in fact, it was the Northern Lights. I couldn't see it with my naked eye.
Oh.
It wasn't that bright, but the camera did pick it up because I had a long enough exposure. And so, yes, the aurora can be seen from as south as Wyoming.
We've seen it a few times here, back 20 years ago, plus or minus.
There have been some since. There's a whole network of people. I don't know. Jan Hayes used to be a part of it, but there was a whole network of people that would get a series of calls before we had emails. And there'd be a network of people calling other people to get them out to go look at the Northern Lights.
Wow. Yeah.
Yeah. Didn't happen.
I would love to. Yeah, I would love to eventually drive north, maybe into Canada, to try to glimpse them. I know there's a place on the East Coast called Algonquin Provincial Park. And I heard it's like an incredible dark night sky, and you're far north enough to see the Northern Lights.
Northern Minnesota is the same way, like around the Boundary Waters canoe area.
Okay.
There, it's not very populated, and the Northern Lights are, or at least when I was growing up and going to college and beyond, they were very common, very visible.
I see. Yeah, so look, in fact, even Wikipedia has given like these KP indices to show sort of like the lower limit of where you can see the Northern Lights. It just so happens to pass right through Jackson, Wyoming, this northwest portion of Wyoming here. So yeah, Jackson's very lucky. But anyway, we'll talk about Magellan here. And so you hear signals from deep in outer space, and these frequent intervals, and it's like, oh, we might be receiving a message. And that's what the Arecibo was responsible for figuring out. And it got me wondering, because I'd watched a YouTube video earlier for like, what are the chances of interacting with intelligent life outside of the solar system? And this is an ongoing debate of whether or not we're alone in the universe. And if we're not, when can we expect a message from other visitors? Or why haven't we already received a message or contact of some sort? And this video I watched brought up a really cool concept called the anthropic principle. And when I was reading, it says that it's not really fair for humans to kind of come up with a probability of the, the probability of the emergence of intelligent life. Emergence is the word I was looking for. So yeah, we're trying to determine this statistically how probable intelligent life can come to be. And we're a little bit biased, it seems. So this is the video I looked up. Okay, let's start here.
From Magellan?
Yeah. So this is a different video, just called The Odds of Life and Intelligence, and really sparked my curiosity here. So let me know if you guys can hear this.
No. Can't hear it. This is the Drake equation.
Sort of, yeah, based on it.
They have two kinds. Some of the stuff that I get in college just goes to the throat.
When you add the probability of intelligence, it decreases the probability quite a bit, right?
Yeah, exactly. So, who's to say that the probability of life emerging, given, or I should say, intelligent life emerging, giving the proper conditions for life to flourish, why should that be so close to one? So it's sort of controversial.
Just taking into account the Goldilocks, what do you call it?
Goldilocks zones. Yeah,
Zones.
they are.
Yes.
I'm trying to figure out something else. No, this is just really- or it's too full. They're not the bowl, so. Yeah, the bowl, of course. I don't want it in that bowl. I want to put it somewhere.
One of the things that it's very hard to find out if we ever find out the answer to is how long should we expect intelligent life to form once it's possible for life to form in the first place? For us, it took a few billion years. It may be the case that, okay, life, you're all set. You can get started whenever you want. You're in the Goldilocks zone. It may take maybe trillions of years for intelligent life to finally emerge. Maybe we just got lucky and we did it really quickly. It's like, or you can make the assumption that no, when life is ready to happen, it's going to happen pretty much immediately.
How is intelligent life defined or understood, or is it not understood?
I don't think it's a hard and fast definition, but if you had asked me, like, what qualifies as intelligent life?
Yeah.
I would imagine life where you can make the intent to communicate. So under your own control, you make the decision, say, I want to communicate. I have some idea and I need to share it. That would be more or less my requirement for you to be considered an intelligent life form. Viruses or something other than whose only job is to just invade a cell and replicate. It's like, okay, yeah, that's like a job it has to do, but is that voluntary? Surely you're spreading your information, but that's like the only thing you do, and it's sort of autonomous at that point.
I believe that it is the viruses, wouldn't they be seen as opportunistic?
And could you call trees intelligent, or flowers, or fungus? I would say not really, because they don't really express their choice to, I don't know, grow to be 50 or 100 feet tall. Whereas I can tell you a chimpanzee, for instance, is intelligent because it wants to tell its friend, hey, look, we have bananas up in this tree, we should go get some. And I can use hand signals or gestures to convey that. Humans are definitely intelligent because we're conveying information back and forth. I'm doing that right now.
Although I was listening to, some other philosopher, I'm reading this book on philosophy of mind, and she was talking about this work about Venus flytraps.
Oh, yeah.
That they have to discriminate between closing on a bug as opposed to closing when they're touched by rain or anything else. So they are making decisions about the environment.
That's a really, really good example. Yeah, maybe I would throw that under the umbrella of an intelligent organism. It has the capability of deciding whether or not to close its trap. So yeah, but the big question is, like, as this video addressed, is how long should it take for intelligent life, whatever you want to call it, to come about once the conditions are set? And oh yeah, the other thing I wanted to mention is sort of our chances of communicating with some extraterrestrial. So let's say we assume this being exists and is able to transmit messages however it wants. What's the probability that we Earthlings encounter it? And I would still say chances are really, really slim. Because even if the universe is abundant with intelligent life, the universe is so gargantuan and it's been around for so long that the chances of us intercepting a message, I think, are still minuscule. Let's say 1 billion years ago, there existed a civilization even more intelligent than us, even more sophisticated. And they were blaring out messages. Hey, look, we're here, we're here. Doesn't matter. It couldn't even have reached us yet because we haven't been around for that long. And the universe is continuing to expand. So if you're in a galaxy outside of the local group and you're trying to beam a message to us at the speed of light saying, hey, look, we're here, we might never, ever get that message because the universe is expanding faster than that message can get to us. It's kind of disappointing, but that's what science is telling us right now.
Yep.
Well, I mean, you're just setting certain parameters in the Drake equation as just very, very low. And that, when you're with everything you're saying. But I guess the only question is, even if you set them very, very low, I think the thing that generally bails out believers on the other side with the Drake equation is just not only the sheer number of planets in this galaxy, but the sheer number of galaxies.
Yeah.
So even if you get it down to there's 1 out of 1,000,000 chances that intelligent life would show up in our galaxy, which is really pretty low, because most of the time people seem to somehow end up with a positive number from that. But even if you say 1 out of 1,000,000 chances in our galaxy, since there's hundreds of billions galaxies, that still should mean there's intelligent life. I mean, you're right. I guess on the other side of it is this issue that's in the Drake equation about how long does the galaxy last, which is kind of the pessimistic. How long does intelligent life last?
Yeah,
because
exactly.
the pessimistic idea is that, once we have the means of destroying ourselves, which we have, this advanced civilizations sadly don't last.
Yeah,
I mean, that's kind of pessimistic. But
right. And if you were to ask me, I would say absolutely. Of course, there should be a large number, in fact, of living organisms out in the universe, and probably intelligent ones. There's just such a huge number. There's over 100 billion galaxies that we know to exist. How could there not be life? The only problem is, like, space is so big that the distances we need to send these messages, sometimes you can just never receive them according to physics as we know it. So it's
mark that one, physics as we know it.
Yeah. So maybe somebody else has a more elegant way of explaining how the universe works. Maybe wormholes are a regular thing elsewhere, and they use it to commute to work.
Well, in this movie, the implication at one point, there was only very little fragments of, it's kind of like painting an abstract painting and just dabbing it with different little brush strokes. So there was that one brush stroke when he touched, the spheres 1 or 2 times, and the feeling that he was in touch with. And then his computer, Ferdinand, got overwhelmed with all the data that was coming in. The implication was, that advanced civilizations have incredible ways of communicating all the time in the universe, and we're not there yet to be able to do it.
Yeah, we can't just understand. We can't get the message. It's too far ahead of us. Yeah, it's always an interesting perspective to have. It got me thinking, because in the movie, when they first discovered, a message is being blared out to them, a guy was like, "Oh, are you talking about a pulsar?" And pulsars, if we ever encounter some kind of message in the future, are very much like regular, almost like a Morse code, bits of information just being fired out at us. And pulsars, I think, are extremely interesting objects in the universe. They're like lighthouses. They're beacons in the universe. And what they are they're spinning neutron stars. And they're spinning incredibly rapidly. And neutron stars themselves are extreme objects where we're not even sure what the composition of them are when you get down into the core. This is one of my
how far away they are?
The pulsars can be tens of thousands of light years away. and they still have these really powerful radio waves. That's what they're sending out. This is one of my favorite YouTube videos because hardly anybody gets to grasp just how extreme a neutron star really is.
Stuart, this looks like something Stephen Stahl would create.
Mm-hmm.
Is this our sun?
Mm-hmm.
Stars that are more massive than our sun.
Got
So
it.
our sun will not do this. It's not massive enough.
Jeez. Wow.
Yeah. Yeah. Go on.
Are we still talking about
Neutron
pulsars?
stars.
Huh?
Yeah, neutron stars.
Is that the same as
A
pulsars?
pulsar is just a spinning neutron star.
Got it.
This does not seem like a place to go on a vacation.
Absolutely not.
Or an exploratory trip yet.
One of the coolest things, I don't know if they mentioned this in the video, but if you were to visit a neutron star, and let's say you could stand up, if you fell from a 5-foot ledge, you would hit the ground at about 4 million miles per hour.
Now that's gravity.
Yeah. Extraordinarily dense. So yeah, when you get to the core of neutron stars, where scientists are very uncertain what the constituents are. So we just call it like this quark gluon soup. And it's really just a huge question mark.
And you know what gluons are, Owen?
I couldn't tell you precisely why.
It's kind of like gravitons that carry gravity. Gluons carry this strong force that essentially keeps
Things
Works
together.
together.
protons and neutrons together in atoms.
Got it.
It's one of the four forces.
Wow. Is it a force?
Mm-hmm.
So
Okay.
yeah, it's a force carrier.
Just like a photon carries electromagnetic waves,
Yeah.
and a graviton, which we have not been able to identify yet, carries gravitational waves. A gluon carries this strong force that glues together protons and neutrons.
Yeah, I think gluons are also responsible for keeping the quarks together. So if you cut open a neutron, you would actually find 3 more little balls of these quarks, up, down, and down quark. Yeah. Strange stuff.
Mm.
What else do I want to look at?
There's no theoretical reason, is there, that quarks can have constituents, or is there?
Yeah, we think, according to the standard model, that's it. Once you hit quark, you're really done. There's no more splitting it up anymore.
Mm-hmm.
But we don't really know. There's so many mysteries just inside this little standard model. One crazy thing, if you look just at the quarks themselves, is why is the top quark so heavy compared to the rest? So you look at these numbers. For example, the up quark is 2 mega electron volts per c squared. This is just a unit of mass.
Mhm.
The top quark is 100,000 times more massive than the up quark. And we don't really know why. And it also decays really fast, I think. We've only been able to keep it going for 10 to the minus 25 seconds. That's the mean lifetime of the top quark.
Don't blink.
10 to the minus 25. Let me see.
That's a lot smaller than the life of a Higgs boson, which is 10 to the minus 22.
Yeah, so we're talking about like septillionths of a second.
Mm-hmm.
I don't even know if they have a prefix for that. I think it's like a zeptosecond. Oh yeah. A tenth of a yoctosecond. because 10 to the minus 24 is a Yaktov second.
Is it
Never
measured?
Heard that before.
I mean, yeah, apparently. I don't know how they measure that. A time, it said roughly, they have to give an estimate when it gets that small. But, you combine some of these quarks together and you have a proton, and when its mean lifetime is, it's more than 10 to the 29 years. It's pretty much immortal. So that is, oh my goodness, 200 octillion years. That's the lower bound of a proton's lifetime.
Wow.
That will be here till the end of time. The proton. You can't kill the proton. All you need is 2 up quarks and a down quark.
What happens to protons in a neutron star?
So the protons actually merge with the electrons because the pressure is so great, and they become neutrons. Yeah.
Well, we're just very lucky that protons are stable, or we wouldn't be here.
True.
Back to the anthropic principle.
Right. Mm-hmm.
It's interesting when I think about all these particles and all this stuff that's scattered around the universe. And I think about, I don't want to say UV rays or whatever. There's various rays and various onslaughts our Earth has with whatever's coming in from outer space, by way of particles and air and you name it. I keep thinking that I wonder how much of this has to do with our evolutionary development based on the impact on our cells and DNA and the changes that that you can undergo with some of these particles. Cancerous cells, for instance, but I don't think cancerous cells is the only way we change.
Well, yeah, I think humans evolved the way we did because of the Earth's conditions. Like if the Earth had been maybe a little warmer or a little less protected by the sun or even a little colder, then I think human bodies would look a little different and we'd be more susceptible to some things and more resilient to other things.
Mm-hmm.
So I don't think it's like a coincidence that we have eyes that are sensitive to visible light and we have skin to protect us from UV radiation and so forth. I think it's the reverse. I think Earth's conditions created us.
Well, that's pure Darwinism. It's basically survival of the fittest, being able to survive, the fittest surviving in the environment of,
right. And that's
it's not just the biology, the environment of the physics as well.
Yeah, that's why polar bears are polar. They live in the Arctic, and we have elephants, that are completely hairless, live in the savannah by the equator. I don't think that's really a coincidence. There's one more thing that I read actually before the movie, and I said, oh, you know what, this has a good segue, I think. So if you have, like in the movie, a crew traveling for an extended period of time, let's say for years, aboard some sort of spaceship, we want to figure out what is it like staying that long outside of Earth. And I think we had gone over something similar, like how is your mental state, and how can you
Mhm.
cooperate with other people when you're isolated for so long. But there's a really important part that I overlooked, and it's something called chronesthesia. What is your sense of time when you're away from normal daylight cycles? And this is the little article I had read before even watching the movie. And I think it was super interesting. So this is an account of somebody who had lived in the dark, who had lived in the dark for, I don't remember how long. Let me double check here. And he writes
An adult
in the dark.
was a fully grown human being?
Yes.
Or was it a child?
Here it is. Let me read this to you. Okay. 1963, French geologist Michel Siffre went into a cave and spent more than 2 months without daylight, and he wanted to investigate his sense of time, chronesthesia. And he would call up scientists every so often who were on the surface, and they recorded the time, the actual time of the call, but they never told him what the real time was. And so he says, quote, 42nd awakening, I really seem to have no least idea of the passage of time. This morning, for example, after telephoning to the surface and talking for a while, I wondered how long that telephone conversation lasted and couldn't even make the wildest guess. 52nd awakening. So you assume 10 days later, I am losing all notion of time. When I telephone the surface and tell them what time I think it is, thinking maybe only an hour has passed between my waking up and eating, it could be 4 or 5 hours that really have gone by. And it's something I can't even explain. I believe the idea of time I have at the time I'm calling them, but if I called an hour earlier, I would still have stated the same figure. I have no idea what I did today. It cost me a real intellectual effort to recall such things. So the outside observers were recording that, he would sleep and wake up and go back on a period of about 24 hours. But he had no idea how long it was. When he thought it was August 20th, it was really September 14th. He had underestimated by almost half the length of my working or waking hours.
Wow.
A day that he really thought was like 7 hours was really 14 hours. So you can really throw off your biological clock when you remove these normal cycles of daylight and nighttime.
Well, you've got your melatonin, your hormonal, your circadian rhythms, I'm sure the rest of the cortisol levels all being haywire. I don't know what the research has shown for what happens with people who go through that, but when we were out in northern Minnesota and Canada in the winter time, taking winter camping trips, this was back in 69, 70, 71. The sun was setting at about 3:30 in the afternoon. And we would get back to our camp after hiking out, et cetera, and everything took so long. Everything was just incredibly slow just because of the cold. And but we would go to bed at 6 o'clock in the evening and get up at 6 o'clock in the morning. And we would need to have that amount of sleep just because of the energy we were expending.
Yeah, it's profound. I think, Stuart, you'd also mentioned when we're talking about this, like how you're away from the normal daylight cycles, the people in Antarctica, how they have to live when they're doing their work at the station, because, you know, in the summer months, like right now, they're not getting any daylight. It's pretty much perpetually dark at this time of year in Antarctica. So I would never imagine living in such a place.
Well, we've had, I've had numerous mental health colleagues, psychologists and psychiatrists, who've gone up to work in Alaska, and they all end up on lights. They all end up with a seasonal affective disorder because the lights change. The weather isn't quite as extreme, except I think Fairbanks is extreme, and they do fly over to the Nome area and that. But in Anchorage, for instance, most of them were on lights because they had to regulate their mood and their workload and their, you know, stuff.
So just shifting, since I have to leave in 6 or 7 minutes, what other thoughts did you have about the movie, Ryan?
I think, you know, the movie had gotten like maybe a little too excited. I think more excited than I would expect in reality if we had heard a signal from somewhere else. You know, would my first instinct be to fly out and try to investigate what it is, or just like sit tight and await whatever is coming to us, if it's coming to us?
Mm-hmm.
What year was this movie made?
2017.
2017. I like the way they simplified it so simply that this guy was mostly without a spacesuit, mostly in an oxygenated area, you know, almost unrealistic environmental portrayals given 2017.
Yeah.
Yeah.
I mean, I think they were doing it as kind of a
But that wasn't the point.
modern art. It was a takeoff. It was, you know, almost like, you know, yeah, because in some ways you'd think this movie would have been made in 1970 or something, you know, but, you know, it's almost like they use these things as comic. It's almost like they knew they were being absurd, but that was okay in terms of the point they were trying to make.
Yeah, I think it was a more artistic film rather than a truly realistic film where you're trying to replicate, you know, what would actually happen in such a scenario.
Yeah.
But movies are allowed to do that.
I mean, it's
And I guess-
interesting because of what was portrayed in movies like, what's the one that Sandra Bullock and George Clooney were in?
Gravity.
Because they had much more up-to-date portrayal of the sophisticated machinery, etc.
I think that Ryan is right, that this was more, they were exploring certain themes, like, you know, if extraterrestrial, you know, it's the same theme that we've seen in many things, you know, do we connect with them, you know, and even touch it as the astronaut did, or you have the Department of Defense guy saying, this is dangerous. These people are out to get us.
Yeah.
And then I guess the dialect of relationships, you know, that he left his wife and it was painful. And at the end, even when he had a chance to go back to her, he left her again for his exploration. So it's connection versus exploration was another theme they were.
Yeah.
And then why did they call it Ferdinand Magellan? I mean, I guess there's a lot just in that name of a great explorer of the world from the 1500s.
Yeah, that's what I thought. I think Magellan was the first to circumnavigate the globe. So yeah, such a historic event, I guess, would be connected to, one of the first people to venture this far out into the solar system. I think I could see a reasonable connection there.
They, that quote they had at the end, I was telling Oanne about it today. I'm not sure I understood why they put it there. That T.S. Eliot
T.S.
quote.
Eliot quote.
We shall not cease our exploring, and at the end we shall arrive the place we first started and know it for the first time. I'm not sure I understood what that had to do with.
Yeah, I was kind of wondering. I think it just kind of goes with the artistic theme of it. Not quite sure.
But it was worth a watch, and Oanne doesn't like gory horror stuff, so this was
slimy arms and floating blood. In fact, that's what when he came across, when he was reaching his hand in, I said, "Oh no, are we going to get a slimy arm coming up?" It's so interesting because the simplicity of this movie is almost half its beauty.
I guess they were into themes about AI to some extent with Ferdinand and control, the same kind of theme with Hal in 2001, and who was in this, I guess the question is who was controlling Ferdinand at certain points.
It was either AI or the guys on Earth.
Yeah. Or the Chinese, I don't know.
The other thing about this movie was that the time factor, the time factor in communication was so instantaneous compared to, the 8 years you would expect for a message to get out to Neptune.
Well, didn't they say an hour and 20 minutes at the speed of light or something?
That makes sense. To travel to Saturn by the speed of light from the sun would be an hour.
Yeah.
I think to Uranus, it's maybe closer to 2 hours, though.
Mm-hmm. Neptune, they went to Neptune.
But Neptune, yeah, is over 2 hours at least.
Right.
Yeah. But it was very interesting. I'm glad we saw it.
Yeah.
So that is basically the slides I wanted to present today. The cool things about pulsars, something called the anthropic principle, which is when it comes to exploring extraterrestrial life, and then how humans fare when we don't have clocks or biological cues.
Oh, those were good points.
There is one biological clue that came out in the news today. It had to do with the laundry, and instead of just throwing clothes away after they became too rancid for close living, that they're working with Procter and Gamble as to how they can clean the clothing that the astronauts use up on the space station and elsewhere, because they're preparing for a longer life. I just had to bring that up. It came out. I saw it in the news today.
So, see you next week.
All right, Stuart. See you. Take care.
Take care. Have a good one.